Welcome back everyone. In this lecture, we will begin with handshaking lemma, which is a very fundamental result in basic graph theory. So, let me actually state the result. So, let us start with the graph G. So, then we want to actually compare the degree of the vertices, the sum of the degree of the vertices and the number of edges. So, we have this following very basic identity. So, which tells, so let me state it as a theorem. So, if we take the summation, the degree of the vertex V and we sum it over all possible vertices of G. So, then that summation is going to be equal to twice the number of edges. Okay. So, recall that the degree of the vertex, the d of V, is nothing but the number of edges incident with the vertex V. So, that means we are having the vertex V here and then we are looking at all possible edges that are incident with that vertex. So, then that is called the degree of V. So, now you sum all possible degrees of a given graph G whose vertex set is capital V. So, then that summation is going to be exactly equal to the twice the number of edges. So, this epsilon is nothing but the number of edges of G. Okay, how do we prove this? The proof is actually very simple counting argument. So, you count the same object in two different ways, that is what we are going to do, and probably that counting we will use this incidence matrix and do it, then it will become much more clear. So, let us look at the proof. For the proof, what you do? You take this incidence matrix. So, takes this incidence matrix which is denoted by M, and recall that it is indexed by the vertices and edges, and then we put this entry Mij either 0, 1 or 2 that like represent. So, let us recall this is that matrix Mij. So, where Mij it is the number that comes from 0, 1 or 2 basically. So, this number of times that Vi and Ej are incident. So, that is what it counts. For example, if it is a loop, Ej is a loop at Vi, then we get actually this Mij to be 2, and Vi and Ej are not incident, then we get that Mij to be 0, and otherwise we get 1. So, this number either 0 or 1 or 2. So, this is our incidence matrix. So, now if you take this incidence matrix and then what we can do, we can look at the sum of the entries of all the entries of this incidence matrix. So, that now, so let us look at this matrix. So, it looks like something like this. So, now what we are going to do, we are going to look at the sum of the entries in the row corresponding to vertex V. Okay, if you fix a vertex and then you sum, you fix a vertex here because the rows corresponds to the vertices. So, the rows corresponds to the vertices, and then the columns, they corresponds to edges. So, if I fix one vertex V and then look at the sum of the entries in that particular row, so then it is easy to see. So, this is going to be exactly d of V. So, then what you do, you record all possible row sums here. So that is going to be for each vertex the degree of that vertex. So like d of v1 etc. d of vn, that is what you get. Then if you take sum of all possible this row sums, so sum of these row sums, that is going to be exactly the summation d of v, v and v. So that is what you get which is there in the left side. But this is also sum of all entries in M. So this is exactly sum of all entries in M, which is again equal to sum of all column sums. Okay. What one can do? One can actually look at all possible column sums. So you just pick a column and then sum that entries here, and then what you get is the column sums. Then the sum of column sums will be equal to sum of the row sums, which will be equal to sum of all entries in M. So that tells that the summation dv v in v is supposed to be sum of all entries in M, and it is easy to see that this is exactly going to be twice the number of edges. So this is exactly equal to twice the number of edges. Okay. So that tells the summation dv v in v is equal to twice the number of edges. So that is because each of the epsilon column sums of M is exactly 2. So if I look at one particular column and then look at its column sum, okay, corresponding to an edge, it is exactly 2, because that is the like that is apparently clear from the definition of incident matrix. Okay, so that is how you get the sum of column sums to be exactly twice the number of edges, which is exactly the sum of dv v and v. Okay, then if we have this identity, you can use this identity to prove immediately that the number of vertices of odd degree, that must be even. So as an corollary, so in any graph, so the number of vertices of odd degree is exactly even. Okay, so how do we prove that? So let us look at Vi. So Vi be the set of vertices of like I degree in G. So where I is either odd or even. Okay, so let me write it like this. So V1 is nothing but the set of vertices of odd degree in G. Okay. Similarly, we can define V2 to be the set of vertices of even degree in G. So then what we get immediately, V is nothing but V1 disjoint union V2. So in particularly the degree sum is can be rewritten as follows. So the summation degree of V in V1 plus summation degree of V in V2. So this is going to be exactly equal to twice the number of edges. So now since the elements that are coming from V2 have a degree even, so when you go modulo 2, so they are all going to be congruent to 0 modulo 2. So that would imply immediately that the summation d of V in V2 is congruent to 0 modulo 2, because sum of even is nothing but even. But what happens to the odd? So if V is in V1, so then the degree of V is going to be of the form some 2r plus 1. So that means d of V is congruent to 1 modulo 2. So so in particular if you sum it over V in V1, so then this is going to be congruent to summation 1 V1 comes from V1 modulo 2, because all the numbers that we are having this twice R goes to congruent to 0. So, maybe let me write it like this, this is exactly twice RV. So, summation dV V in V1 is exactly equal to summation twice RV V in V1 plus summation 1 V in V1. So, that tells that this quantity is equal to twice summation RV V in V1 plus the number of vertices in V1. Okay. So, this tells that the summation dV VV V1 is plus summation dV V in V2 is exactly congruent to the number of vertices in V1 modulo 2. But this is exactly equal to twice epsilon. So, that means number of vertices of odd degree must be congruent to 0 modulo 2. So, this implies that number of vertices in V1 is 0 modulo 2. So, that is the same as saying the number of vertices of odd degree is even. So, this is a very strong restriction that we have about the number of vertices of odd degree. Okay. So, let me actually define some important notions that one actually defines for any graph, and these notions again will be used later in order to study some particular properties of graphs. So, let me just go through all this definition. So, first let us start with what is a walk in G. So, a walk in G, okay. So, it is a finite non-null sequence. So, let me write it properly, is a finite non-null sequence of the form, okay. Let us denote it by W. So, V naught, E1, V1, E2, V2, etc., EK, VK. So, basically we have these vertices Vi and these edges Ej such that, so the terms are alternatively vertices and edges, and the ends of Ei are nothing but Vi minus 1 and Vi. So, we have something like this, okay. We have V naught, then from here we go to V1, then you have E1. So, then you go to V2, but this V1, V2 is E2, okay, like that. But the thing is there is no restriction among these vertices and edges in the walk. So, it can repeat, it may not repeat and so on, okay. So, let us put it in more proper word. So, it is a finite non-null sequence of this form V naught E1, V1 etc., EK, VK, whose terms are alternatively vertices and edges, okay, such that for 1 less than or equal to I less than or equal to K, so the ends of this Ei are nothing but Vi minus 1 and Vi. So, this is the edge that we are talking about, Vi minus 1 and Vi should be the edge Ei for each I from 1 less than or equal to K. Okay, in that case you call that as a walk. So, we also say that W is a walk from V naught to Vk, or sometimes we just simply call it as V naught Vk walk. Okay. So, these are all some notations used in graph theory. Okay. So, we can also define the origin and terminus of this given walk. So, V naught is called the origin and V k is called the terminus of this W. And all these vertices V1 etc. Vk minus 1 they are all called internal vertices. So, these are all called internal vertices of W. And what is k? K is the length of this W. Okay. So, you have this W which is given by V naught E1, V1 etc. Ek Vk, k minus 1 is there. So, this the number of edges, that is what you call it as the length of the walk. And like I said, in a walk the vertices can repeat, edges can repeat and so on. So, there is no restriction in the walks. So, we can actually define some basic operations among walks. For example, if I start with a walk W which is of the form E naught V1, E1 V1 etc. Vk minus 1 Ek Vk. So, then what we can do, we can define what is called reverse walk. So, which we denoted by W inverse. So, the reverse walk is defined to be Vk Ek Vk minus 1 etc. V1 E1 V naught. So, this is what you called as reverse walk or inverse walk. And now, if we take two walks, okay, such that the terminus of first walk is origin of the second walk. So, let us call them W and W dash. So, W is V naught E1 V1 etc. Vk minus 1 Ek Vk, and W dash it begins with Vk, Vk Ek plus 1 Vk plus 1 etc. Let us say it is end with some ELVL. So, then what we can do, we can actually define this new walk called concatenation of these W and W dash, which is denoted by this you write one next to each other W W dash, and by concatenating this W and W dash we get this W W dash, which by definition you just join them. So, which is given by V naught E1 V1 etc. Vk minus 1 Ek Vk, then you add this Ek plus 1 Vk plus 1 etc. ELVL. Okay. And this is this new walk that starts with V naught and ends with VL. So, one can also define a section of a walk. So, suppose if I start with W which is of the form V naught E1 V1 etc. Ek Vk. So, then what we can do, we can stop at some point. Okay. So, because we are keep tracking the edges. So, the walk should always end with vertex. So, you cut it at some vertex. So, that you call it as a section. So, the section is nothing but V naught E1 V1 etc. some Ej Vj, where j is less than k. Okay. So, this you call a section of W, and we can actually cut it in the front as well as the back. So, one can also cut it here again. So, then we will have again smaller section. So, that also we call it as a section. So, for example, it can start with some Vi, Ei plus 1, Vi plus 1 etc. and then end with Vj, okay, where I is strictly less than j and greater than or equal to 1 and less than or equal to k. So, you choose something like this, and this is also you call it as a section of W. Okay, these operations on walks are very intuitive. So, we no need to explain the further. So, what happens in a simple graph? A walk is indeed determined by the sequence of the vertices. So, hence a walk in a simple graph can be specified by its vertex sequence only. So, we do not need to write down the edges, okay, because edges are determined by the vertices, the end points of the edges. So, we do not need to really write down these extra edges in a simple graph. So, in addition, if we actually take all of these edges, they are all distinct, then you call that walk a trial. Okay. So, what is a trial? So, trial to begin with, it is a walk. Let us say it is like of the form W V naught E1 V1 etc. EK VK. So, you assume that all this E1 etc. EK, they are all distinct. Okay. As I said before, vertices and edges in given walk need not be distinct, but if you put that assumption that edges are distinct, then that you call it as a trial. Okay. So, what is a path? Path is, in addition, you also assume that the vertices of given trial is actually distinct. Okay. So, path, so it is a trial distinct. So, not only that, additionally you assume that the vertices that are involved V naught etc. Vk, they are also distinct. So, that is what you call it as a path. Okay. And it is easy to write down example where you can distinguish walk, trial, path and so on, but these are all some very basic intuitive technical terms which are one should be careful with using them. So, to be on same dictionary, so I have spelled them out. Okay. We can actually define the notion of connectedness among graphs. Okay. So, we can talk about a connected graph and then connected partition of a graph and so on. So, first we will define what is connected, then it will become clear, like any given graph can be written as a disjoint union of its connected components. So, first let us start with the notion of connectedness. So, the notion of connectedness of graph like so they are, so you may study later in topology that connectedness of subsets of R2. So, if you draw the graph inside your R2, which is the plane, so then the connectedness of the graph is actually kind of reflects the connectedness that you see it in as a subsets of R2. So, basically intuitively what you want to call it as a connected set. So, given any 2 points, you should be able to go from one point to another point. That means, you need to find a path within the set that actually connects a given 2 points. So, that is what you take it as a definition of connected graph. So, you first say that two vertices u and v of G are connected if there is a path between u and v, and you actually define a graph to be connected if any two vertices are connected by a path. Okay. So, a graph G is connected if any two vertices u and v of G are connected by uv path. Okay. So, you have graph G and then you have this uv. So, you need to find a path that actually connects this u and v. in that case you call that graph is connected. So, now how do you actually write any given graph as union of connected components? So, this connection which is actually finding a path between given two vertices. So, that defines an equivalence relation on the vertex set. So, you take the vertex set, you define this relation, okay, for u comma v in V, u is related to V if there exists a path between u and V. So, then it is an easy exercise to prove that this is indeed an equivalence relation. So, now what happens, this V will be partitioned into equivalence classes, let us say there are k of them, then each subgraph spanned by this Vi is going to be connected, and this G will be, now if you think about it, it will be union of or disjoint union of all these subgraphs spanned by Vi, and each one of them will be connected. So, this is all of them are connected, and this is what you call it as a connected partition of G, and this is like it is a unique decomposition of G into connected components. So, what is the meaning of that? That means these Vi's up to permutation, so they are uniquely determined by the graph that you start with. Okay, so, because this is coming from this equivalence relation, so there is no ambiguity in between. Okay, so there are like easy characterization of this connectedness. Maybe I will leave one statement as exercise. We can say that G is connected if and only if for every partition of V into two non-empty subsets V1 and V2. So, then what will happen between them, if you take subgraph spanned by that V1 and V2, then we will be able to always find an edge from one component to another component. Okay. So, let us start with any disjoint partition of given V. Both of them are non-empty, let us say V1 non-empty as well as V2 non-empty. So, then you have GV1 here and then we have GV2 here. So, if original G is connected, then what you can do, you can always find an edge between this given this component GV1 and GV2. Okay. So, that is the exercise, that is easy to prove. So, show that G is connected if and only if, so for any partition, okay, for any non-trivial partition V into V1 disjoint union V2, there is an edge with one end in V1 with one end in V1 and one end in V2, okay, like this, what is shown in the picture. So, that is always true. Okay. So, another important thing, the matrix for example, that I have introduced before, the adjacency matrix. So, that records all information about the graph. So, in particularly the number of walks between given two vertices. So, that is also recorded using that adjacency matrix. Indeed, one can prove the following interesting fact. So, you can show that this is very interesting exercise. This is just test actually the definition of adjacency matrix, whether you have understood or not. So, I am leaving it to you. So, show that the number of this Vi Vj walks So, you are fixing two vertices Vi and Vj of length k. Okay, we are fixing the length as well. In G is nothing but the ijth entry of this A power k. So, where A is nothing but that adjacency matrix of G. Okay, this is not very hard exercise, so I am leaving it to you to check this. Okay, so I will stop here, and then we will actually start with some other notions like cycles and so on in the next class. Then we will slowly move into what is called Eulerian tour, and then when it exists and so on we will see in the next class. I will stop here. Thank you.